Hello everyone, welcome back to this tutorial again. So you can see here in previous tutorial we have studied about the slope deflection method, and we have just studied the introduction and one of the simple problem of toe span uh, as an example for that. So in today's session we are going to study about the overhanging beam problem. So in this problem you can see on your screen it has been displayed. We need to draw shear force diagram, bending moment diagram for this particular beam which has been shown. So the procedure and other thing will remain very much similar. So first of all we need to calculate fixed end moments, that is MFAB, MFBA. So these values, these are the formulas, standard formulas are there. According to this we need to calculate. Next you can see after calculating this fixed end moments, remember to calculate the fixed end moment for a overhanging span, you can see 10 into 2, that is 20, and it is in anti-clockwise direction, so we are going to consider it as a negative, okay, as it is a overhanging beam. Next you can see I am going to apply slope deflection equation one by one. So MFAB, so this is the slope deflection equation. Again you can see at point A there is a fixity, so slope at point A will be equal to 0. So our equilibrium conditions will be like this: slope at point A will be equal to 0, moment at B will be equal and opposite, means they are equal to 0. Similarly at C we can consider. Now we move forward. So after applying the slope deflection equation, I am going to get this equation, and similarly I am going to apply the slope deflection equation for MBA. So it is nothing but MFBA plus 2EI divided by L into 2 theta A plus theta B. So in same way I am going to apply and I am going to calculate this equation. Similarly next span I am going to consider MBC is equal to MFBC plus 2EI by L into 2 theta B plus theta C. So in same way after doing this I'm going to get the equation like this over here. Similarly for this, so remember there is no need to apply the equilibrium condition for overhanging span. So applying the equilibrium, sorry, there is no need to apply the slope deflection equation for overhanging span. So applying the equilibrium equation, so MBA plus MBC, you can see at joint B there are two moments which are acting, MBA and MBC. So these two moments should balance this particular span. So to balance that particular span, we are going to consider these moments as a equal and opposite moments. So I am going to consider the equilibrium equation as shown here. So after considering this equilibrium, as shown here, after considering this equilibrium equation, I am going to substitute MBA and MBC equations. So after substituting in this equation, final equation I have got like this, and I am going to name this equation as equation number 1. Similarly at joint C, in the same way I am going to apply the equation. I am going to substitute MCB and MCD values are equations to get the final equation like this. Now you can see theta B and theta C. Theta B and theta C are the two unknowns. So I am having two unknowns and two equations. After solving these two unknowns and two equations, I am going to get theta B and theta C. After this, to calculate the final moments, I am having these equations. You can see this one and this one, this, and these theta values. I am going to substitute these theta values in those equations to get MAB, MBA, MBC, and that means final moments. So these final moments I am having. And after this, I need to calculate shear force and I need to calculate bending moment. So to calculate the shear force and bending moment, I need to calculate the support reactions. To calculate those support reactions, I am going to apply the equilibrium conditions and other things, which is very much similar to the moment distribution method which we have studied previously. So after calculating the reactions, I am going to draw the shear force diagram like this. and after that I am going to draw the bending moment diagram like this. So bending moment diagram, you know that it is a combination of final movements diagram and free movement diagram. I'm going to combine this and I'm going to draw the bending moment diagram. Elastic curve is the curve which shows the deflection of the curve after applying the loads. So this is the elastic curve for the diagram. I hope you have understood this problem. Go through this problem in detail. If any problems you are going to arrive at, please let me know. So further in this video, we are going to study about the sinking support problems. So when the support sinks, there is a only condition which we have to apply. There is a only change which is going to occur in the formula is minus 3 delta divided by L. Remember, delta is negative when the right support sinks and delta is positive when left support sinks. Means this whole equation 3 delta divided by L is negative when right support sinks, and if left support sinks, this equation will be positive. So it is plus 3 delta divided by L. So to understand it better, let us consider an example. So analyze the continuous beam by slope deflection method. The support B, remember this support B sinks by 5 mm. So draw a bending moment diagram, elastic curve and shear force diagram. Take EI value is equal to 2 into 10 to the power 4 kilonewton mm square. Remember it is kilonewton, it is given in kilonewton and it is given in mm. So we need to convert it to meters. So first step will remain same, calculation of fixed end moments. Remember, there is no change in calculation of fixed end moments. In case of moment distribution method, we have changed the fixed end moment calculations when the support sinks, but here there will be no change. The only change which we are going to arrive at is this particular one. So you can see MAB is equal to MFAB plus 2EI by L 2 theta A plus theta B minus, remember it is minus. Why? Because you can see span AB, right support sinks. So this particular equation will be minus 3 delta divided by L. So delta is given in mm, so I am going to convert it into meters. So I have converted it into meters and I have kept and I have marked this equation like this. Next, MPA. Here also the span AB is there, so this term will remain as a negative only. Next, you can see if I consider the span BC, this term should be positive, because you can see if I consider the span B and C, B is a left support. If left support sinks, this should be positive. So finally we have considered this as a delta as a negative, and negative plus negative we have made it as a positive. So it is MBC. Remember, this is a very important point. Next, you can see again negative they have made it as a positive as this span is MBC. As the span is BC. Next, apply the equilibrium equations. So at joint B, the MBA and MBC both should be equal and opposite, and their sum should be equal to 0. Again, here you can see MCB plus MCD. At this joint we have considered MCB and MCD. Both the moments should be equal and opposite, and their sum should be equal to 0. So at point B, we have considered this equation and we have substituted the equations which we have got. So this and this. So after substituting these equations, I am going to get the final equation like this, and this is I am going to mark as equation number 1. So at joint C, you can see if I substitute these two MCB and MCD, I am going to get this equation, and the final equation will be like this, and I am going to mark it as equation number 2. Now again, two equations, two unknowns. I can calculate theta B and theta C very easily. So substituting in the equations, we can calculate the final moments. So rest other thing will remain same. Calculate the support reactions, calculate shear force, and calculate bending moment diagram, and draw the elastic occur. So rest other things will remain same. This is the only change which we are going to occur when there will be sinking support. So that is 3 delta by L. So minus 3 delta by L we are going to consider when right support sinks, plus 3 delta by L we are going to consider when left support sinks. Okay, we will move further. I'll just take a basic example of non-sway portal frame. So portal frame examples are also very simple. So this is a portal frame which I am going to consider. For this we need to draw the bending moment diagram. So fixed end moments calculation will remain same. Slope deflection equation will also remain same. Everything else will remain same. There is no change. It's a very simple type of problem. So you can go through it. If you are arriving at any difficulties, please let me know. I'm going to upload this notes with the videos in Google Classroom. If any problems are there, please contact me. Thank you.